So the theme of this series is complex behavior from simple rules. And I'm going to talk about a particular example of this, which is the relationship between chaos and order. This is now classic modern physics. It's very interesting and very profound. And I hope you will enjoy it. Now, let me start off by explaining how you can get chaos from order or order from chaos. It's really very simple. There you go. Jim Schilling, an emeritus professor in our department, reminded me of the existence of this old, this is actually, Jim took a picture of a piece of paper and then sent it to me via email. I'm not sure if he's here in St. Louis or he's in Germany right now. But anyway, I thought that was an appropriate way to start off. There's a little bit more to the story than this. And it starts back a fairly long time ago with a guy named Pierre-Simon Laplace, the Marquis de Laplace, okay? So the Marquis de Laplace was a very important guy. He lived through a very turbulent time in French history, and he was honored by Napoleon as being a great scientist. And then after Napoleon was gone and there was the Bourbon Restoration, he was made a marquis, all right, a nobleman. He made lots of fundamental discoveries. He's sometimes referred to as the French Newton, okay? And he's considered one of the greatest scientists of all time. He gave us a lot of different things. I can't say that he was a mathematician who did a lot of physics or a physicist who did a lot of mathematics. He was good at just about everything he did, and he did a lot of different things, including some experiments. For example, did some work on the speed of sound. He wrote a 5-volume set of books on celestial mechanics, which really set the standard, which was the starting point for the modern theory of celestial mechanics. Newton, had put the theory of celestial mechanics on a firm footing. The planets, the stars, they all moved according to Newton's laws. But it was Laplace who came in and he said, well, what happens when the planets interact via the gravitational force? How do we model this? How do we include this in our calculations? Why does the moon only show one face towards the Earth? What's behind all that sophisticated behavior? But for our purposes today, he also gave us a very clear, fundamental, early statement of something called causal determinism. And here it is in one form. And he says, we may regard the present state of the universe as the effect of its past and the cause of its future. An intellect, this is what became known as Laplace's demon. He did not use that terminology. An intellect, which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed. In other words, he knows the initial starting point, knows what's going on at a certain time, where everything is and how much its mass is and everything else. If this intellect were also vast enough to submit these data to analysis, in other words, to apply Newton's laws, say, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom, For such an intellect, nothing would be uncertain, and the future, just like the past, could be present before its eyes. So this is a very strong form of classical determinism seen through the eyes of someone with vast knowledge of how classical mechanics works. And he said, give me a system, give me the initial conditions, give me the laws under which the system evolves, and I'll tell you what its future behavior is like. Okay? And this is a very common position. You see it a lot in various aspects of human life. You see it in the stock market. You see it as a belief about the weather. You see it as a belief about all kinds of things, but it's actually wrong. So there's a kind of behavior in classical systems which we refer to as chaotic, or we say it's undergoing chaos. And it's behavior that looks random, but is nevertheless guided by deterministic physical laws. And it is kind of strange. It's a little bit unfamiliar, I think, if you've never seen it before, but it goes way back. So I will say a little bit more about Henri Poincaré towards the end of this, but it really started with Poincaré, who was a great, great mathematical physicist. Perhaps not as important as Pierre-Simon Laplace, but certainly right up there, very close. And it didn't go too far. But in the 1970s, a guy named Mitchell Feigenbaum did some work at Los Alamos National Laboratory, which led to a rebirth of interest in this chaotic behavior. And that's mostly what I'm going to talk about today. But really what we're doing is we're starting with a great truth about the way the world works. The classical world, driving our cars, looking out the window and seeing if it's snowing or sleeting or raining. Thank you all for coming out today. I wasn't sure if maybe I'd be talking to, empty chairs. The weather's been pretty bad. In classical physics, the world is governed by these deterministic laws, and we actually understand almost all of these laws. We understand the laws that govern the weather, but somehow something prevents us from predicting the future. And that particular thing that prevents us from predicting the future, at least too far in advance, is chaos. And this book by James Gleick, who's a very, very good science writer, was first published in 1987, and it's gone through many editions now. This is, I think, the anniversary edition, and it's very good. And if you want to know a lot of the history, this is an excellent book. And you see the butterfly on the cover, which has particular meaning in the theory of chaos. Now, when I'm talking about chaos, what do I mean exactly? What I mean is this. In a lot of purely classical systems, important systems, we see this kind of apparently random behavior, even though we know it's governed by simple, really, laws of physics. For example, this is a picture from a NASA study in which you see a plane and it's going through smoke. I'm not sure if it's going through it or whether it is emitting it. But what you see is that there is a vortex, like a tornado sort of, that seems to be coming from or associated with the wingtip of the plane, right? And it certainly doesn't look like it's some sort of smooth pattern. It looks very complicated. In fact, we know that these kinds of vortices or turbulent behavior are necessary for plane flight. There's a sort of a facile explanation that you'll see, maybe you learned it in high school or in college, that says that there's a law, Bernoulli's law, that is responsible for wings being able to provide us with the ability to fly. It's wrong. There's no good way to say it. It turns out that you have to have turbulent flow to get lift, okay? And that's the reason why wings on airplanes have trailing edges, is to provide that the vortices off of the wings. Now here, you're seeing an American submarine, and you can see the two kinds of fluid flow that we usually talk about. If you look at the front of the ship, the bow of the ship, you see that the waves are sort of moving smoothly up the bow, and they're breaking because of course they're moving up out of the water, but it's kind of smooth behavior. But then if you look at the sides of the boat, you see that there's this churn, right? The smooth behavior, okay, is laminar flow. The fluid moves in sheets. And the frothy stuff is the turbulent behavior. And the transition from laminar behavior to turbulent behavior is a key property of many, many systems, including modeling airplanes, but also, for example, in studying airflow around cars and trucks. And if we understood this better, presumably we could do a lot better job of designing systems to have the properties we want. So, this is a really important problem that, literally hundreds of billions of dollars, probably over the course of the last 50 years, billions of dollars have been invested in.
Mike?
Yeah.
So you said airplane flight has to have turbulence.
It has to have vorticity.
So you have to have the vortexes off the wingtips?
Yeah.
But they put the sharklets on the wingtips in order to minimize the vortexes. And what about, I always thought it was like a percentage of, say 70% Newton action reaction and maybe a bit of.
Yeah, that goes back to the Bernoulli's law explanation.
Exactly.
The wind is moving, yeah, but it's
Not necessarily Bernoulli, just particles hit the underside.
It's not right. There's a theorem that relates the lift of a wing to, it's a theorem in complex variables, so it's just fluid mechanics. Okay, and it says that the lift that the wing feels is essentially the total vorticity of the fluid flow around
I've
the
heard of
wing.
it before, but I don't remember. What is the name of it? Okay.
Golly, it's been so long since I taught that course that I forgot. It's,
All right.
it's the theorem that says
I
that.
stumped you, I'll shut
It's
up.
the theorem that says that, yeah. Okay, now, here's a more familiar example. I think at this point, we're really familiar with it. We've had some interesting weather here. We can predict climate for the next 100 years, or at least we think we can with some accuracy, but not the weather next month. It's, how many people remember when there was a 7-day forecast? Right, and now there's a 10-day forecast. Why is there now a 10-day forecast? Well, it's because computers have gotten more powerful. But why, if they've gotten more powerful, why have we been stuck on 10 days? Why not 12 days? Why not a whole 2 weeks? Well, the answer is that the forecasts are not reliable. We throw more computer power, but we do not, at the problem, but we do not get more accurate forecasts. And this too is a manifestation of chaotic behavior. You see, when we talk about climate as opposed to weather, we're talking about the long-term weather patterns. We're talking about things like the temperature of the ocean, the temperature of the air, the average yearly temperature. And these things are largely determined by conservation laws, basic physical principles that are, rock bottom physics. We don't violate conservation of energy, right? The energy has to come from somewhere, it has to go somewhere, right? And as long as you stick to those, you're in pretty good shape. But the details, the day-to-day, month-to-month, even year-to-year behavior depends on factors that we can't predict. And weather is subject to the butterfly effect. Remember the butterfly on the cover of the book? The butterfly effect is a nickname for what we also call sensitive dependence on initial conditions. That is to say, small changes now lead to big changes in the future, which we can't predict. And that is the hallmark of chaotic behavior. It's also a staple of science fiction movies, right? So the idea is, the time traveler gets in his time machine, he goes back to the days of the dinosaurs, he steps on a butterfly. He goes back to the future, and all of a sudden, instead of his beautiful fiancée and other people, it turns out civilization is composed of dinosaurs. Well, maybe it doesn't really actually work that way, especially the time machine part. But the idea is pretty clear. We have some knowledge that we don't have accurately. We do not have infinite accuracy as to our current state. We don't know what the wind is doing perfectly everywhere in Missouri or in California. And this is the thing that limits us both in our weather predictions, our multi-day forecasts, but it also has effects long-term about the global stability of the climate. We try to make predictions about what the next 50 years are like, but we find out that things are surprising us. It's hotter than the predictions we made this year. It's the hottest year ever, in spite of how cold it is right now in St. Louis, right? And so this is a fundamental limitation too, and it's every bit as important as turbulence, maybe more important, right? And of course, we also see chaotic behavior in human affairs. People like to think that the stock market is made up of, literally millions of rational people making rational decisions. Economists know that that's not true. They understand that there's a psychology to investing. And one of the best, most popular books about the stock market ever is a book by Burton Malkiel, A Random Walk Down Wall Street. And what he explains is that a lot of the market is in fact random. We cannot discern the pattern. And there are other places where we actually use chaos, or we use some sort of pseudo randomness. How many of you ever played Legend of Zelda? Come on. Yeah. Okay. Right? Well, if you remember the old video games, the oldest video games used to ask you to enter the date and time. Why did they do that? Well, video games are fundamentally deterministic. Computer programs are deterministic. So the only thing you can do to give people a different game experience is to have some different input every time, otherwise you'll get the same game. And so in the very oldest games, they would ask you to enter the date and time, and they would use that as a seed to start the game off in a random configuration. But it wasn't really random. If you came back to a day later and you entered yesterday's date and time, you would get the same game. And that's actually how the games work now. That's actually how computer programs that seem to use random behavior work. They use what are called pseudo-random number generators that take a given seed. They got more sophisticated. They can read the system clock, so they don't have to ask you to enter the number. They use random seeds, and then you get a bunch of numbers that appear to be random, but they're actually deterministic. Okay, so we're actually using the fact that a pseudo-random number generator is just a little subroutine sort of thing. Takes a deterministic process and appears to produce random numbers, right? So that's also a very important thing in all kinds of areas. So, this kind of behavior is everywhere. Sometimes it's good, like video games. Sometimes it's sort of strange, like the stock market. And sometimes it's just absolutely crucial to modern life. So there's a lot of interest in chaotic behavior. It's important. And that's where Mitch Feigenbaum comes in. Now, you may notice that he has a little kind of a stare there. That's in most of the pictures of him. I met him in, oh golly, I think it was the late 70s at Los Alamos. I was visiting there. My advisor and I were both there, and he introduced me to Mitch. And Mitch had very startlingly blue eyes. And he was sort of a very intense person. Unusually, he was a smoker. Yeah, he just kind of looked like that. But what Mitch did was he was trained as a high energy theorist, and somehow he decided he was going to look at chaotic systems. And he started studying the behavior of simple, what are called chaotic maps, which I'll describe in just a minute. And they didn't have a lot in the way of computer resources. I remember when the first handheld calculators came out that actually were able to do math. The first one was an HP calculator, wasn't this model, but it could add, subtract, multiply, divide, and take the square root. It was $400. Professors everywhere were trying to figure out, how can I get $400 out of my grant so that I can buy this marvelous tool of science, right? And so what Mitch had was not some sophisticated device. He had something that was a little fancier than the original calculator. If you look very closely, it could do 1 over x, y to the x, the y-th root of x, cosine tangents, very fancy, an HP 65. And it was the fact that he was using this HP 65 that allowed him to make this discovery, because he was just doing, this numerical analysis of how certain behaviors emerged mathematically, how chaos emerged. And as he worked through these numbers, I mean, you can imagine it's just like sitting there at your desk and putting numbers in the calculator. No programmable, no computers, just him and the calculator. And he noticed that the display would show certain numbers over and over again, or numbers that were close to that number. And so there was a pattern. And so he tried different chaotic behaviors, and he still got the same numbers. And, I mean, the tools weren't sophisticated, but Mitch was. And he said, oh, there's something going on here. Okay? So he figured out why. But it was such an unusual work that it actually, although it was done about 1975, it was not published until 1978. People did not know what it was about. They did not know what to make of it. But eventually, people realized what was going on, and he got a MacArthur Fellowship. Remember, the Genius Prize is still around. The Wolf Prize, one of the greatest American awards for contributions to physics. The Wolf Prize was actually for some experimental work he did with a collaborator in which they studied chaotic behavior in melted, I think it was melted salt. They looked at turbulent patterns, or the transition to turbulent behavior in a melted salt. And the experiments confirmed his theoretical work. And that's that they both got the Wolf Prize. And then a few years after that, quite a while, he got the Heinemann Prize, which is the foremost American award for theoretical physics. So this was important work. And that's what I'm going to tell you about next. So this is a simple description of how we think about models. And it really follows what Laplace suggested. He said, well, we have some initial data, some input that describes the way the system is now. We have a model, some laws that are mathematical or algorithmic that describe how this system evolves in time. And out of that, we get predictions about the future. And, these can be very simple models, or they can be very complicated models. And exactly what the model is depends on who's asking. If you're a climate science, the sun is just more or less a black box, providing somewhat variable energy to the Earth. You're not concerned about the solar corona, the solar atmosphere, how nuclear fusion works. It's just a big thing that shines. Okay? For an astrophysicist, the sun is a complicated, important system that's worthy of study on its own, right? So there's a degree of abstraction in any model, right? We simplify what we're going to study by specifying the model. Now, I'm going to start with population growth. This is what we call a linear model. And here's the equation. It's very complicated. It says that if you want the number of people, or I don't know, foxes, whatever, moose, in one generation, you take the number in the previous generation and you multiply it by a number C. So C is a parameter that we specify, and X1 is the initial condition. It's where you're starting from. And if C were 2, then we would say that the number of moose doubles every generation. So you start with 2 moose, presumably a girl moose and a boy moose, and then you got 4 moose. Then you get 8, then you get 16, then you get 32. So this is just exponential population growth. This is also how compound interest works. It turns out that the mathematics of moose and the mathematics of higher finance have a certain overlap, okay? So that's pretty simple. If you take C less than 1, then the population is declining, right? You get fewer and fewer moose every year, and pretty soon you get a fractional moose, and that's just not realistic. So the moose die out of this population. This is also how radioactive decay works. The half-life is the period over which half of a sample decays. So rather than say that it's a generation of population, I can say that, if I go from one half-life to the next, the population of radioactive nuclei in a given sample decays by half. That's definition of what a half-life is. You know, so you start off with 100%, then you get 50%, then 25%, 12.5%, et cetera. It's pretty simple, it's deterministic. By the way, if you want a nuclear reactor, you want C to be exactly 1. Because if you let X be the number of neutrons produced in a reactor at any given moment, if C is less than 1, then the number of neutrons will die out and the reactor will cease to produce energy. If C is greater than 1, then the number of neutrons will increase rapidly and you no longer have a reactor, you have an entirely different problem, okay? So C equals 1 is actually kind of an unstable point here, okay? But normally we just say, okay, well, it grows or it shrinks, I get it. Now, this is not actually how real populations work. They work in complicated ways. So what we're going to do is we're going to change this model just a little bit to model another feature of real populations. And this is an equation called the logistic equation. If you look at it, the first part is exactly what I had before, C times the previous generation, X sub n. And then there's a little factor, which is 1 minus X sub n. That's the additional part that makes this a highly non-trivial equation. Okay. Okay. So again, X1 is the input and C is a parameter. And for X small and C greater than 1, well, if X is small, this is pretty close to exponential growth because this is just 1 and we just ignore this part. But if you get close to X being close to 1, then all of a sudden the growth turns into decrease because this factor of 1 minus X is an additional factor. So if X is 0.5, you know, you think of the 1 as being 100% capacity of the environment that the moose or whatever are living in. And so all of a sudden that's an extra factor of 0.5 and the population starts to shrink. So you can see how attractive this is, right? It models in the effects of the environment so that there will be some equilibrium population of moose, of people, whatever you're studying, and you'll get either growth to the equilibrium point or you'll get a decrease to the equilibrium point. And either way, that's fine. We understand that. So this is modeling something that's a little more realistic in the world, in the real world behavior. I wish I could get rid of this little bar across the top, but apparently I can't. But this is exponential decay to what we call a fixed point of the transformation. So this is the number of generations, and I'm starting with a C of 1.5. So that's bigger than C equals 1, but I've got this factor 1 minus X that, you know, makes the population decrease if it gets too big. And what you see is that if I start with a population that's big, 0.5, or if I start with an initial value that's low, 0.2, either way, over the generations, they converge to a line. And once I get there, I pretty much stay there. I do stay there. It's a stable fixed point of the system. And you go, oh yeah, okay, great. I understand how this works. You know, it's, you know, the resources determine how many moose or people or whatever can live in a given environment. And that's great. I understand that. Nice stable behavior. But if you increase the value of C, it gets a little bit different. Start with the same initial values and something happens. It starts, instead of smoothly decaying, it starts kind of bouncing back and forth, right? And so we call this exponential decay with an oscillation, because it's going back and forth. And in fact, you see that you're kind of going back and forth between the same numbers, but you know, they're kind of out of sync with each other, the two populations. And you're saying, oh, okay, I understand that. If the population's a little bit low, then it becomes high the next generation. And if it's a little high, then it becomes low the next generation. And eventually you get to where you're going, to that stable point. Except if you increase C a little more, you don't. You get what's called bistable behavior, where the same initial values, and now you're going back between a high and a low, high and a low, high and a low, high and a low. And it just goes back like that. So what you've done is you don't have a stable point, you have a stable two cycle, right? Where, you know, imagine a stock market, where 1 year was a good year and 1 year was a bad year. 1 year was a good year, 1 year was a bad year. Well, everybody would know what to do. So it'd still be okay. Now, what happens when we increase C a little more? Well, here's a higher value of C, and what do you think happens? Well, you all see the pattern in the behavior now, don't you? Well, I don't. Two different values, and you know, it looks completely right. It does look like the stock market, right? You don't know exactly where it's going. I can't make a prediction. It's really pretty complicated. Now you might think that there are some sophisticated data methods that allow you to analyze this, and you can figure out what this is going to do. That there's some pattern that we just can't see somehow, but that's not so. Suppose I take two different values and they're really close, 0.2 and 0.21. I could choose them closer, you know, 0.2 and 0.2001. And the same thing would eventually happen, but this is enough to show you what's going. So same value of C, except that my initial values, the red and the blue, are very close. And from the first generation to the second generation, not much different. By the third generation, you start to see some differences, more with the fifth, more with the seventh, but by about the ninth generation, it looks completely random again. This is the butterfly effect. This is sensitive dependence on initial conditions. No matter how close you make the two initial points, the futures diverge at some point in the future. This is why we cannot predict the weather reliably more than 10 days in advance. It's not because our computers aren't good enough, it's because we don't know the initial conditions well enough. Now, I don't think you can go out in your backyard and or don't step on butterflies, please don't. Okay, but you know, I don't think you can go out in your backyard and wave your hand and all of a sudden, you know, a month later you get snow. That sounds more like magic than science, but this is really the effect, and it's really surprising. Now, there's another way of plotting this information, which is to plot the long-term equilibrium behavior of the system. Okay, and this was sort of a key thing that Mitch realized. For C up to a certain point, just below 3 C equals 3, you get a stable fixed point. So if you go out some, you know, long distance, 100 generations, you've got a pretty good idea of where that stable fixed point is. Actually, it's analytically calculable. Just calculate it. But you reach a certain point, and all of a sudden, the stable fixed point bifurcates into a stable two cycles. So what's really happening is you're bouncing back here to here, here to here, here to here, here to here, here to here. That's that two cycle behavior, right? So the individual points aren't stable, but you're stable going back and forth between them. Then you go a little bit further, just a little bit beyond 3.4, and you get this purple behavior where there's another bifurcation, and you have a stable 4 cycle. So they kind of go 1, 3, 2, 4, 1, 3, 2, 4. And then beyond that, there's a stable 8 cycle. Hard to see, but it's in there. And then eventually you get to a point about here where the behavior is completely chaotic. So this is the secret behavior that's embedded in this kind of map. And it's sort of a universal transition to chaos in that you don't have to look at the logistic map. You can look at lots of different kinds of maps and you'll still see the same behavior. You won't get the same points at which the different bifurcations happen, and you won't get the same points, but the overall pattern, 1 becomes a 2 cycle, 2 cycle becomes a 4 cycle, 4 cycle becomes an 8 cycle. That's universal behavior. And that's why Mitch and his collaborators got the Wolf Prize, is because they looked at the behavior of convection in a metallic salt, and they saw 1 becomes 2, 2 becomes 4, 4 becomes 8. They saw the same behavior experimentally that the theory predicted.
What parameter were they varying?
Heat, temperature. Yeah, it's you take a large pan of something and you get these convective rolls and you look for doubling of the rolls. So you have the hot and cold going like this, and then the number of cells increases. So this is what's called a pitchfork bifurcation, where you go from, say, a stable fixed point to a 1 cycle. And I won't spend a lot of time on this because it's a little technical. But what happens is there's still a fixed point here, but it's an unstable point. And the stable behavior is now this 2 cycle, and then it becomes a 4 cycle over and over again. And it's kind of related to this kind of geometry. Imagine that you've got a ball in a hill and it rolls down the hill and it's stable at the bottom of the hill. But then you've got two hills, and there's a hill in between. And now if you put a ball here, it rolls down here, it rolls down there. And these are both stable, but that's unstable. It's sort of a profound paradigm in physical science today. Called spontaneous symmetry breaking. But you don't really need to know that. So I just included this because it's kind of pretty, and it shows you, this pitchfork bifurcation behavior, and it shows you the intricate patterns that are buried in this behavior here. There's a lot more. There's a lot of beautiful mathematics in chaotic systems, which is in fact accessible to, say, high school mathematics. It's all algebra. It's not complicated calculus or anything.
Good question.
Sure.
Just because you've got a couple of very simple expressions that give you that, you add the 1 minus the multiplication. Where isn't there a leap to say, well, this is how real systems work, who says that? I mean, how do we know that?
I'm going to talk about that. Well, so in the convective cells, the experiment I described, that's governed by the Navier-Stokes equation. But I will come back to the point. Excellent. Now, it turns out that there's more buried in this. So if you look at this kind of behavior, and you measure the distance, the change in C, where you get the first bifurcation, then you get the second, then you get the fourth, right? Then you can look at the difference between these lengths. Right, and they're always getting smaller, okay? And if you look at the ratio of these distances, it turns out that no matter what map you start with, you eventually get to a universal number, which is 4.669201, 609, 1029, it goes on, okay? We don't know if it's an irrational number. It's suspected that it is. In fact, it's suspected it's a transcendental number like pi, but Feigenbaum found it because he was working on the calculator. So if you do it with the logistic map, you get 4.2337 for the ratios, 4.551, 4 points, and you're converging to this. And you sort of see, well, eventually I'm going to get to 6692, right? And now we have very sophisticated theories that predict that calculate it. And so we know it to, arbitrary precision, but we don't know a lot about, the nature of the number itself. And there are other universal numbers that are buried in this theory. Now, I'm going to address your question in a little bit more detail. So remember, I mentioned this guy, Henri Poincaré, another great French mathematician, mathematical physicist. And he was a tremendous figure at the beginning of the 20th century. And he made fundamental contributions to relativity, both special and general relativity. And he proposed the Poincaré recurrence theorem, which is a fundamental theorem in statistical mechanics and the behavior of thermal equilibriums, systems in thermal equilibrium. It predicted the existence of gravitational waves in 1905. Took a while to detect them, but now we know they're real. But he also worked on the three-body problem. How many people have watched the three-body problem? Yeah, okay. So you kind of know what it is. And he was interested in just, something simple like the sun, earth, moon, and the stability of the system, right? It's an obvious problem to work on. It's a hard problem to work on. And he discovered the first chaotic deterministic system using a tool which is now called the Poincaré section. And here's the idea. Imagine that, you have a planet going around the sun, right? And you don't quite end up where you started from, right? So if I draw a plane through a given section of between the sun and forever, and I say, okay, every time the planet goes by, let's say it's the Earth, every time the Earth goes by, I make a little mark, and then it comes around again, and I make a little mark, and I keep track of where the Earth is when it crosses this imaginary plane. That's what the Poincaré section is. And you see, by doing that, what he was doing was he was reducing the very complicated details of the orbit to a simple map that says X, well, next year it'll be at P of X. Next year it'll be at P of P of X, right? And you see, that's the idea of reducing very complicated motion to a very simple recurrence relation. And so what we've done is we've reduced the model, which is very, very complicated, to something that's rather simple. And we can study the simple map rather than the more complicated, more general problem. There's a related map, which is kind of cool, that's used actually a little bit more. It's called the stroboscopic map. And it works just exactly like you think. Instead of sampling when the Earth passes through a given plane, you flash a strobe, right? This is often used in experimental setups, particularly in small atomic and subatomic systems. We just sample the behavior that we want to study at discrete intervals. It's sampling. okay? And so this simplifies the problem by ignoring most of the details. And that brings me to another point that I wanted to talk about, which is our solar system. We think of the solar system as being a reliable clock, right? The Earth goes around the sun in 365 days. Oh yeah, leap years, and there's some, some adjustments, but we think fundamentally that the stars and the planets are reliable. That their motion is determined, except it's not true. In the time of Laplace and maybe a little bit later, people constructed orreries, which were mechanical models of the motion of the sun, the planets, and sometimes the stars. If you saw Indiana Jones and the Dial of Destiny, that was starred, if you like, an ancient mechanism called the Antikythera mechanism that is believed to be an early form of an orrery, okay? A mechanical model of the planets and the sun. This is what it looked like in the movie. This is what it looks like in real life, okay? It is not a time machine or anything like it. But it turns out that in work done in 1992, Sussman and Wisdom, Sussman, they were both professors of computer science at MIT, showed that in fact the motion of the solar system is in fact chaotic. They did it by building what they called a digital orrery, and they did very, very high precision calculations of the long-term behavior of the planets. And they said, well, what happens if you introduce a small change in the initial conditions? And they're looking at timescales of 100 million years, okay? And what you see is that the difference between two slightly different initial conditions, it starts off small and then it gets large and then it gets very, very large until finally there's no correlation between these two initial conditions that start out very, very similar. So even the heavens are not deterministic systems. Now, I started out talking about a great truth of classical physics. What happens with quantum systems? Quantum systems are in the news, right? IBM just announced Majorana 1, a new chip for quantum computing. AI, certainly the rage. Maybe there'll be a quantum AI processor in our future, I don't know. But the greater truth is that in our quantum world, the laws of physics are still deterministic in the sense that they make definite predictions about the future, but those predictions are inherently probabilistic. We don't know when a given radioactive nucleus will decay. It is apparently just random, really random. So chaotic classical systems are deterministic, but appear random due to this butterfly effect, exponential sensitivity to initial conditions. But what about quantum mechanical systems? Those start out being probabilistic. They have randomness built in. So the classical ideas about chaos do not apply. Does that mean that the whole basis of chaotic behavior is wrong? No, it doesn't. Because there's an important principle of quantum physics, the correspondence principle, that tells us that the classical systems are a particular limit of the quantum systems, and the limit where Planck's constant, the fundamental constant of quantum behavior, goes to zero. And so the question of quantum chaos is, how does classical chaos manifest in a how does classical chaos manifest in a quantum system? And I have to tell you that the answer is that there has been an enormous amount of work, and I think it's fair to say that we do not completely understand this. However, the interest in quantum information in quantum computing, quantum cryptography, and quantum sensing, for example, has really revived interest in these kinds of questions. And I think the progress is really being made now in a way that it was not, has not been happening for a long time. So I'm optimistic that at some point we will have better answers. So, you know, keep tuned. We're on our little journey to infinity and beyond. Except it's mostly inward, mostly not outward into space. Okay, thanks.